In the previous video, we introduced how we can keep track of our angular position in terms of that angle theta and that radial distance from our axis of rotation. In this video, we want to continue with introducing those kinematics variables for rotational motion. So we're going to talk about angular displacement, angular velocity, and then angular acceleration. So I have a little picture here. And so I've got positions noted along a kind of circular path. So this point here, this is our starting point. Then at some time 2, we're here, and at some time 3, we're here. And if we think of this like a motion diagram, I can think about each of those intervals having the same time interval. And so just like we do with a regular motion diagram, right? If I have a motion diagram that looks like this, and I have my set time interval between the two, I can tell that I'm speeding up. So in this particular case, for the rotational motion, I know that this change in position here is less than this change in position here. So this would be an example where the object is speeding up as it is rotating about that x-axis. Okay, so if we look at these, we have our 3 different positions. If I want to express angular velocity, and the variable that we're going to use here is a lowercase Greek omega. So it's not a W, it is you need to draw it kind of like this. So it's a lowercase omega. This is going to be the variable that we use for angular velocity. And we know that in general, velocity is a displacement with respect to time. So if I want an average omega, so I'm going to say omega average, this is going to be a displacement, and omega is an angular velocity, so we need an angular displacement. So this is going to be a delta theta over a delta t. So a change in that angular position over that a time interval, right? So if I again come back to my picture here, I'm going to take 2 and 3 just to keep the picture from getting super messy. So I'm going to say that this is theta 2, and then this is going to be theta 3. And then each of these, R is going to be constant, right? But if I'm thinking about that change in theta, my change in theta is going to be theta 3 minus theta 2. So my delta theta is theta 3 minus theta 2. So that's going to give me this angle here, right? This angle in between that 0.2 and 0.3. So that's going to give me my average angular velocity. If we do the same thing that we did with our linear velocity, and we want to know an instantaneous omega, so I can say that omega is going to be what I get when I take the limit as this delta t approaches 0. So lim as delta t goes to 0, delta theta, delta t, and that's just going to give me d theta dt, right? So this is going to be my instantaneous angular velocity. So these are 2 equations that we'll be using. The SI unit for angular velocity is going to be radian per second. So if we look at our here, right, if we just look at our units, so my delta theta, so if it's in SI, so that's radians, and my time is radian per second. Sometimes you will see for an angular velocity, so I'll put these down here. So we have radians per second. Sometimes you will just have an inverse second. So remember, sometimes the radian is not written. So sometimes it is inferred. So you might have radians per second. You might have just an inverse second. We also can have revolutions per second, revolutions per minute, right? And this is RPM. If you see that, that's revolutions per minute. You could also have degrees per second or degrees per minute. So there are a lot of different units that we can have when we're thinking about angular velocity. The important thing to recognize is that if we are going to connect it back to any linear quantities, we need to get it back into that radians per second. So that is our SI unit. When we think about omega or angular velocity, we do need to indicate a direction. And so for that, oftentimes we will say counterclockwise is positive. This is how we can indicate that. in a given problem, you can change that, right? You can say that clockwise is positive. So you can do either way. In general, we like to assume that counterclockwise is positive. So that's probably what you'll see the most if you're working through problems. But we do need to indicate that. So we can indicate that using just put the positive and then just indicate what direction you are saying positive is going to be. Angular acceleration is our last quantity that we want to introduce. In angular acceleration, we are going to use the variable alpha. So alpha is what we're going to use for angular acceleration. And if I have an angular acceleration, just like linear acceleration, that comes from a changing velocity, right? So we have a alpha. So I'll say A. So A was dv dt, right? So alpha is going to be d omega dt. So they're analogous types of quantities. This is going to tell me the rate at which omega changes. The SI unit here is radians per second squared. But just like with omega, we can have all of these different variations, right? I can have an inverse second squared, revolutions per second squared, revolutions per minute squared, or degrees per second squared. You can have any of those variations. It's just going to kind of depend on the problem that you're working with. So you just need to always have that kind of context.